which is on the vectors, yeah, as what we can see from the CI that have represented to you just now. The very first week will be just dedicated towards revision, but hopefully we can finish it earlier, and so that we can proceed with the EMT, the actual lectures of EMT, yeah, in this first week of the lectures. Okay, for lecture number 1, the topics will be revision and vectors, in which the reference for this lecture, you can find it from Sadiku, the book of Sadiku, the first reference just now, page number 3 to page number 27. And motivation of this lecture is to enable the students to refresh the knowledge on the vectors and its operation. So that should be the main motivation, yeah, main objective. So just to ensure that you can still have a good foundations, yeah, in vectors and also its operation. Because why? Because in EMT, most of the parameters, most of the variables that you're going to see in EMT are vectors. For instance, electric field is given by these vectors of E. The magnetic field is given by the vectors of H. Okay, the electric flux density is given by the vector of D. The magnetic flux density is given by the vector of B. So based on this, we can see that most of the parameters that you're going to see in EMT later on will be vectors. And that is why we need to have a good understanding, yeah, good grip in vectors topic, yeah. Okay, so vectors basically is a component which has a magnitude and also a direction, okay, as opposed to a scalar component where it only has the scalar value or magnitude value. Okay, so for a vectors, let's say we have 2 points, point A and point B. Okay, so the vectors of AB basically will be a vectors which is directed from point A to point B, yeah, which is basically given by the arrow. Yeah, the arrow will be the direction of the vectors, which will be from the point of A to the point of B. And we can also have another vectors, which is the vectors of B to A, which is the vectors directed from the point of B to the point of A. Yeah, so the vectors is just given by this arrow, the initial point and the end point. Yeah. Okay, so I'm going to simplify our lectures, in which we're going to see on few topics only, but we're going to have some exercises just to ensure that you can understand the things that you're going to discuss in this vector topics. Yeah. Okay, for the vectors operation, we're going to have a look on the vector components in rectangular coordinates. Okay, that's the first one. And then we're going to have a look at the vector multiplication, the dot product, and then we're going to have a cross product, which is also a type of vector multiplication. Yeah. Okay, so let's have a look at this slide where we have the vector components in rectangular coordinate. Yeah, so rectangular coordinate is actually represented by the x, y, and z coordinate. Yeah, x stands for the x-axis, y-axis, and z is the x-axis. So if we base on this figure, we have 2 points here. We have point of A and we have the point of B, where the point of A is given by a point of 2, 4, and 5 in Cartesian or rectangular, and also point of B is given by 4, 5, and 6. So based on the given points here, we need to find these parameters, the AB vector, the magnitude of AB, and the unit vector of AB. Okay, unit vector of AB. And similarly, we need to find the BA vector, the BA magnitude, and also the R unit vector or unit vector of BA. Okay. Okay, so let's have a look at the AB vector. The AB vector basically will be this vector directed from the point of A to the point of B. And based on this, we can see that the AB vector, yeah, the AB vector shall be given by x, which is 4 minus 2, component of x. So 4 minus 2 will be direction of x, plus 5 minus 4, okay, in the direction of y, and z6 minus 5 in the direction of z. So that should be the AB, in which we're going to have it as 2 direction of x plus y plus z. direction. So that should be the EB vector, yeah? Okay. Right, and from here we can calculate the AB magnitude, yeah? The magnitude of AB vector, in which from here we can have it as square root of the vector squared, which will be 2 squared plus 1 squared for the y component plus 1 squared for the z component. So end up going to have it as square root of 6. Yeah. So that should be the magnitude of the AB vectors. Yeah. And then for the unit vector is the smallest component or smallest unit of the vectors. So they're going to have it as RAB, or R unit vector of AB, is actually given by the equation of AB vector divided by AB magnitude. Okay, and that should be based on these values that we have calculated earlier. And we're going to have it as 2 direction of x plus y in component plus z component divided by magnitude, which is set of 6. Okay, so that should be the vector for the AB. And similarly, we can obtain the BE vector, yeah, the BE vector, in which we're going to have that the BE vector, okay, will be this direction of vectors, which is from point B to point of A. Okay, the arrow must be pointed from B to A, in which we're going to have it as 2 minus 4, yeah, the x coordinate for the A minus the x coordinate for the B. So 2 minus 4 direction of x plus 4 minus 5 direction of y plus 5 minus 6 direction of z. So end up we're going to have it as 2 direction of negative x minus direction of y minus direction of z. Okay, and from here we can straight away find the BA magnitude, in which I believe that the magnitude should be the same as AB before. Yeah, so we have 2 squared plus 1 squared plus 1 squared based on these vectors given here or obtained here. Yeah, so we're going to have a set of 6, and finally we can find the unit vector for the BA, where we're going to have it as 2 of negative x minus direction of y minus direction of z divided by set of 6. So that should be our unit vector for the BA. Okay, so this is a revision only, just to ensure that you can still recall what is vectors, what is magnitude of vectors, and what is unit vectors. Yeah. Okay, so let's have a look at this example. Let's have a look at just few examples only, not all of it. Okay, let us have a look at part B, which is the addition of the vectors, yeah, vector addition. But the vector addition basically is based on the addition of two vectors here, mn vectors and mp vectors. So we need to find the mn vectors first. So mn is a vector directed from the point of m to the point of n. Yeah, so that should be our mn vectors. Okay, and these mn vectors will be given by the point of n minus the point of m. Yeah, so that should give us 4 direction of x, minus 5 direction of y, and minus direction of z. So that should be our mn vectors. Yeah. Okay, so 3 minus negative 1 will be 4, negative 3 minus 2 will be negative 5, 0 minus 1 will be negative 1. Yeah. And then for the mp vectors, which will be these vectors here, so mp vectors will be given by negative 2 minus negative 1, which will be negative of x, negative 3 minus 2 will be negative of 5y, and negative 4 minus 1 will be negative 5 of z. Yeah, so that should be the mp vectors. And then we can just add mn and mp, yeah, which is the vector addition, by simply adding the similar components of the vectors, in which the results for this will be 4 plus negative 1 will be 3 of x, negative 5 plus negative 5 will be negative 10 of y, negative 1 of z minus negative 5 of z, sorry, plus, yeah, negative 1 of z plus negative 5 of z, that will give us negative 6 of z. So that should be the answer for the vector addition. Okay. And for the m vectors, I mean for this vector, for the part E of the questions here, which is on the vector subtraction, Okay, we want to find the magnitude of 2m vectors minus 3n vectors. Okay, so we know that m vectors basically is a vectors in which the starting point is at origin. Yeah, it's at origin. So based on that, we can say that the m vectors will be equal to negative of x plus 2 of y plus z, because we just based on this coordinate of m. Whereas for the n vectors, yeah, we have n vectors there. So n vectors will be equals to 3 of x minus 3 of y, and there is no z component, so that should be the n vectors. So we have 2m minus 3 of n vectors, so that will give us negative 2 of x plus 4 of y plus 2z, which is multiplication for m with 2, and minus 3 of n, which will give us minus 9 of x, and then we have plus 9 of y. So when we subtract, or when we solve for this, we can have it as equals to negative 11 of x, we have plus 13 of y, and 2 of z. Yeah, so that should be the answer for vectors of 2m minus 3n. And since we need to find the magnitude, so we have 2m vectors minus 3n vectors magnitude. So that will give us square root 11 squared plus 13 squared plus 2 squared, and that's going to have it as 121 plus 169 plus 4. Okay, so please proceed for the answers, and you can do it on your own. Yeah, so that's how we calculate the magnitude for the given vectors. Okay, so up to now, we have discussed about vectors by definition. We have calculated a few examples related to vectors, magnitude of the vectors, and unit vectors. And following that, we did a few examples related to the algebraic operations, which include the vector subtraction and vector addition. Yeah. Right. So I think the rest you can solve this on your own. Yeah, because this is something which is very simple, very easy, I believe. Yeah. Right. So let's have a look at the vector multiplication. The first type of vector multiplication, which is a dot product. So dot product is the first type of vector multiplication, and the yield for dot product will be a scalar. Yeah, the yield. So when we have a dot product, the yield of that will be a scalar, yeah, not a vector. So by definition, when we have two vectors, vector A and vector B, which are said to be operated using dot product here, yeah, A dot B. So definition gives us the values of A magnitude multiplied with the B magnitude multiplied with cosine of theta AB, in which if we can sketch it, we can have this is your A vectors, that should be the B vectors. So theta AB basically will be the angle in between A and B vectors. So when we have A dot B, you're going to have A magnitude multiplied with the B magnitude multiplied with cosine of theta AB, in which this value is a scalar component. Yeah? Just a magnitude. There is no vectors involved here. And in terms of rectangular systems, we can write that the A, yeah, we can write that in general, A vectors in Cartesian system can be written as AX, direction of X, plus AY, direction of Y, plus AZ, direction of Z. Yeah, where we have the A in the X component, in the Y component, and in the Z component. And similarly, we have the B vectors can be written as the Bx of X. We have it a By of Y, and we have Bz of Z. Yeah, so that should be the B vectors in the Cartesian systems of coordinate. Yeah. So when we have a dot product A dot B, basically we need to multiply the same components of the vectors, and then we add them together, where we have AX multiplied with the BX, so that should give us AX BX plus multiplication of the Y component, AY times BY, plus multiplication of the Z component, which is EZ and BZ. Okay, so this is the definition, by definition, the dot product in Cartesian system. So if your A vectors and the B vectors, if on this equation here, let's say I label this as equation number 1. If your A and B vectors from equation number 1 are the vectors in Cartesian system, so we can see that equation number 1 and equation number 2 are the same. So 1 and 2 are the same. Okay, so that should be the dot product, yeah, the comparison between the A dot B by definition and the A dot B in Cartesian coordinate system. Okay, so let's have a look at this example. In this example, we have three vertices of a triangle, which are located at the point of A, the point of B, and the point of C. So if I can sketch this coordinate, we have A here should be at 6, -1 and 2. We have point of B here, which is located at -2, 3, and -4. And then finally we have at point of C here, which is located at -3, 1, and 5. So I just sketch this roughly, yeah. So that should be your triangular structure. Okay, triangular structure here. And from here, we need to find the AB vector. So AB vector should be the vectors directed from the point of A to the point of B. So that should be your AB vectors. And then we have for part B, we have AC vectors. So AC vectors should be these vectors here, directed from point A to point C. Okay, let us find these two vectors first. We start with the AB vectors. So from what we have learned previously, straight away we can find out that the AB vectors will be the point of B minus the point of A, which will give us -8 of X plus 4 of Y and -6 of Z. Okay, and then we can also have for the AC vectors, it should give us -9 of X plus 2 of Y, then we have +3 of Z. Okay, so we have successfully calculated the AB and AC vectors, yeah, based on the given diagram here. And the third one is to find the angle of theta BAC at the vertex of A. So the theta BAC at the vertex of A will be these vectors, will be this angle, sorry, this angle. So this angle is the angle of theta BAC. Okay, so that should be the angle that is requested. Right, so how to find this angle of theta BAC? Okay, so we know that from this diagram, we can apply the dot product method, yeah, to find the theta BAC angle, because from these vectors, we have AB vectors, we have AC vectors, yeah, so we can see that from definition of a dot product, we can have AB dot AC, and that should be equals to AB magnitude multiply with AC magnitude, and that should be then multiplied with cosine of theta of BAC. Yeah, the angle which is located in between the two vectors. Okay, so from here we can see that what we have to do now is that we have the AB vectors, we have the AC vectors, and then from here we can find the magnitude straight away. From here we can have it as, sorry, I'm going to use another marker colors here. Let's say on the green color. So we have here we have the AB magnitude will give us square root of 64 plus 16 plus 36. Yeah, whereas for the AC vectors magnitude, we're going to have it as square root of 81 plus 4 plus 9. So that should give us square root of 80 plus 36 will be 116. And for this will give us 85 plus 9 will be a set of 94. Okay, so that should be the magnitude of AB and AC. And we knowing that the AB and AC, both of them are in Cartesian system, so we can use equation number 2 that we have shown earlier, this equation number 2. Yeah, so we have AB and AC from this part A and part B just now. So from here, we can then calculate the AB dot AC, in which this will give us -8 minus 9, sorry, -8 times -9, which will be 72, plus 4 times 2, yeah, 4 times 2, which will be 8, plus -6 times 3, which will be -18. So that should be the results for the AB dot AC for left-hand side. Whereas for the right-hand side, we're going to have a surd of 116 multiply with surd of 94, and then we have cosine of theta BAC. So from this equation, obviously, we can see that there is only one unknown, which is the cosine of theta BAC, in which from here we can see that the theta BAC will be then equals to arc cosine of 80 minus 18, which will be 62, divided by surd of 116 multiplied with surd of 94. Okay, so need your help to calculate this, yeah, on your own. So then you're going to get the angle of theta BAC. Okay, any questions so far? No, yeah? Okay, let's proceed with the next multiplication type of vectors, which is a cross product. So cross product will be the second type of vector multiplication. And the difference between dot and the cross product is that the dot product will give us a scalar, but the cross product will give us a vector. Okay, so that should be the main difference. Okay, by definition, we have the A cross B. The A cross B will give us A magnitude multiply with the B magnitude multiply with sine of theta AB in the direction of normal unit vectors. Yeah, normal unit vectors. So what is mean by this? So when we have two vectors, let's say we have vectors of A, we have the vectors of B in this direction. Yeah, so yeah, we have vectors A and vectors of B. So the results of cross product between A and B will give us another vectors which are said to be located normal with regard to A and B. That's why this is the vectors of A cross B, because if you base on the equation here, the results will be a vector's value or vector's magnitude, okay, which is A multiplied with B multiplied with sine of theta AB, and we have normal in the vector, which means that the results of the A cross B will give us a new vectors which is having a direction in normal with regard to the A and B vectors. Okay, theta AB is the angle here between the B and A vector. So if I can repeat my statement just now, this A cross B, the result of this will give us a new vectors which is having this magnitude. Yeah, this is a magnitude which is A magnitude multiplied with the B magnitude multiplied with sine of theta AB, and the direction of these new vectors is normal with regard to vectors of A and the vectors of B. Okay, that is why if we can relate this to our Cartesian system, yeah, we know that Cartesian system is having three axes. We have x-axis, we have y-axis, and we have z-axis. So if we have x cross y, yeah, x cross y, what should be the result of x cross y? So if you base on this definition of cross product, we know that x cross y will give us z unit vector. Yeah, and the same things happen if we have y cross z. Yeah, y cross z, it will give us x unit vector. And then if we have z cross x, yeah, z cross x, it will give us y unit vectors. Okay, but the other way around, if we have z cross y, yeah, the other way around, yeah, z cross y, so that will give us negative of x. Yeah, if I can write here, z cross y will give us negative of x. And the same things apply if we have y cross x. yeah, y cross x. So that will give us what? It will give us negative of z. And similarly, when we have x cross z, yeah, x cross z, it will give us negative y. Yeah, so x cross z will give us negative y. Okay, so this cross product, we're going to see this regularly, particularly in magnetostatic field later on, yeah, in week 7 onwards. We're going to see a lot of this cross product. Okay, we go back to these lectures of the cross product, yeah. So in a rectangular coordinate system, x, y, z, we can use a matrix determinant method to find the results of cross product, A cross B. Yeah, so matrix determinant, I think you know this method already. So A cross B, what we have to do is that we have to align, yeah, we have to align the A component of the vectors and the B component of the vectors like this, yeah. So we have X component, we have Y component, we have Z component. So we align it, we are going to have A, AX, AY, and AZ, and we have the B, which is BX, BY, and BZ. If we change the orientation, let's say B cross A, yeah, let's say we have B cross A, so we have to change it now. We have BX, BY, and BZ at the top, and the bottom we're going to have AX, AY, and AZ. So it depends on the orientation of the cross product, yeah. Okay, so based on this, if we proceed with the cross product, yeah, this equation, so A cross B, by using a matrix determinant method, you're going to have it as X direction, yeah, X direction. So we're going to have it as A, Y multiplied with BZ minus AZ multiplied with BY. Okay, and then plus. Okay, so for plus, we're going to have it, okay, I'm going to erase this one. Okay, for the Y component, so we have Y component then. So we close this one. So we have BX multiplied with AZ. Okay, and then we minus AX and BZ, yeah. Okay, and plus the third one, which is for the Z component. Okay, for the Z component, we're going to do, we need to close this Z component. So we're going to have a Z component of AX BY minus BX AY. Okay, so that should be the results of your cross product by using a matrix determinant method. So if your A and B,
Doctor,
yeah,
can I ask a question?
yes, please.
Just to make sure for the y component, is it we should put the positive sign or negative sign?
Okay, right. For the Y component, let me go back to Y component, yeah. Okay, for the Y component, we're going to do is that we close this Y component. Okay, so I believe that what you have learned in class from before is that is negative Y, AX multiplied with BZ, and minus BX multiplied with AZ. Am I right?
Yeah.
Yeah, so similar, right? It's the same thing, yeah? I think it should be same thing, okay? All right. So because what I did here is that I want to eliminate negative sign in front of the vectors, in front of the vector. So I just rearrange the location of AX, location of this AX, BZ, and BX, AZ, yeah? Thank you for the question.
Okay, get it, Doctor. Thank you.
Okay, thank you. All right. So if we go back to this slide, if your A and B are in a Cartesian system, yeah, A and B in Cartesian system. So let's say we label this as equation number 1. We label this as equation number 2. So we can see that 1 and 2 should be similar things. Yeah, 1 and 2 should be equal. Yeah, if the A and B here are in Cartesian systems of coordinate. Yeah. Okay then, so let's have a look at the examples which are said to be similar with the previous one. We have the same triangle, I believe. We have A, which is 6, -1 and 2. We have B, which is the point of it is -2, 3 and -4, and C should be here, which is -3, 1 and 5. Okay, so that should be your triangular structure. Yeah, so not very nice my drawing, but hopefully you can understand clearly. Okay, then you need to find the AB cross AC. So the AB is here, okay, and the AC is here. Okay, so based on this vector of AB, yeah, we have AB vector should be equals to yeah, going to have it as -8, yeah, -8 of X plus 4 of Y -6 of Z. For the AC vectors, we're going to have -9 of X plus 2 of Y plus 3 of Z. Okay, since you need to find the AB cross AC, so we need to use equation number 2, yeah? This equation, yeah? Equation number 2. Because if you want to use equation number 1, this equation, we don't have the angle value, the sign, the theta AB. So we cannot simply find the A cross B. So we need to use equation number 2 then, yeah? So that should be based on the matrix determinant method, yeah? So AB cross AC, yeah, so you need to align it clearly. So we have X, we have Y, we have Z. Okay, so we have AB will be -8, we have 4, we have -6, and for the AC we have -9, we have 2, and we have 3. So when we proceed with the matrix determinant, we're going to have X component. Yeah, X component. So please correct me if I'm wrong. So we have 12 minus -12 plus Y. So for the Y, we have we have 54 minus -24. Okay, and then for the Z component, we have -16 minus -36. Okay, so if I did anything wrong here, please let me know, yeah? So then we're going to have it as 24 of X. Then this will give us 78 of Y. And then we have these will give us plus 20 of Z, yeah? So that should be your the cross product of AB and AC. That should be the answer, yeah? All right, and then you need to find for part B, sorry, it should be part B then. That should be part B. The part B should be there. You need to find the unit vector perpendicular to the plane in which the triangle is located. Which means that we need to find out what should be the normal unit vector. Yeah, what should be normal unit vector? That should be the question. Yeah? What should be the normal unit vector which is perpendicular to the plane in which the triangle is located. So how to do this? We can base on the definition of the cross product just now, in which we have the AB cross AC will give us AB magnitude, AC magnitude, sine of theta AB, and in a vector of normal. So if we base on that, we can see that the n unit vector or normal unit vector can be calculated if we can calculate the AB vector cross the AC vector divided by the magnitude, yeah, the magnitude of AB cross AC magnitude. Am I right? Yeah, this is AB, yeah. Because from definition, yeah, this is definition, yeah, of the cross product. Yeah, cross product. So we know that this component here, AB, AC multiplied with sine theta AB, are basically the magnitude of AB cross AC. Am I right? Because we know that the vectors is defined by the vectors is the magnitude of the vectors and the vectors of it. Vectors is the magnitude multiplied with the vectors. The same thing is applied here. The vectors equals to the magnitude multiplied with the unit vectors. That's why we have it here as the magnitude of the vector vector AB cross with vector AC. So from this understanding, we can use the AB cross AC that we have calculated earlier, which from here we can see that the n unit vector, which is normal unit vector, shall be equals to 24 of x plus 78 of y plus 20 of z, which is the vector of AB cross AC, divided by the magnitude of it, which is 24 squared plus 78 squared plus 20 squared. And that should be square root to find the magnitude. Okay, so please solve this calculation on your own. Yes, you need to find the magnitude of these vectors of AB cross AC, and afterwards you must be then able to find out what should be the normal linear vectors that is perpendicular to the plane where the triangular structure is located. Okay then, any questions for this example of the cross product? No, yeah? Okay, so that's the end of vectors revision. Okay, so I'm now going to proceed with lecture 2, in which we are going to proceed with the coordinate system. Yeah, coordinate system, because we still have 1 more hour before we end the class. So I think it's good if we can proceed with these coordinate systems. Yeah. Right. Any question up to now? No. Okay. Good. Okay. Lecture number 2. This is still a revision part. But the topics will be on coordinate systems. Yeah, coordinate systems. The reference for this lecture number 2, you can obtain it from Sadiko, page 30 to page 58. Okay, so motivation of this lecture number 2 basically is to familiarize the students with the common coordinate systems that will be applied in solving electromagnetic problems. Okay, and believe that you have learned this in mathematical courses, yeah, on the coordinate systems. So just to remind you that these coordinate systems are very crucial, yeah, are very crucial because you're going to use it a lot in EMT. So you need to have a very good foundation, very good understanding on these coordinate systems, yeah. Okay. So this will be the objective for this lecture. Number 1, we want the students to be able to understand the importance of coordinate systems, why we need to learn the coordinate systems in solving EMT problems. And number 2, which are the important things in this lecture number 2, which is we want the students to be able to derive the differential length, which is the DL, and then the differential area, which is the DS, and then the differential volume, which is the dV. So these are 3 main parameters that we want the students to understand: the DL, the DS, and the dV for all coordinate systems that you're going to learn in this lecture number 2. Yeah. So basically, there are 3 main systems of coordinate, which are said to be orthogonal. What I mean by orthogonal? Orthogonal means that all the axes are 90 degrees apart. Yeah. 90 degrees apart means it's orthogonal. Yeah. All the axes are 90 degrees with each other. Okay. So basically, we need the students to understand why we need to learn the coordinate systems. Yeah. So the reason why is that the EMT problems can be in many forms. Yeah, can be in many forms. So what we have here, I just project 3 examples, yeah, of EMT problems. Number 1, let's say we assume that we have a cable. Yeah, we have a cable. Let's say we have this cable, electrical cable or transmission line cable, which said to carry a current of I. And we know that current is source of field. Yeah, source of field. Specifically, is a source of magnetic field. Yeah, magnetic field. So we can find the field at any position, let's say at the point of A, for instance, at the point of B, at the point of C, at any point. Let's say also we can find it inside the cable itself. So if you base on this, if I want to use the equation, yeah, there's a specific equation that can be used to calculate the magnetic field in this particular structure, in which I'm going to use the law of Biot-Savart. Okay, I just project the equation. Yeah, just project the equation where we have the H vector shall be equals to I dl vector cross R integration divided by 4 pi R to the power of 3. So this is the equation of Biot-Savart. Yeah, Biot-Savart. They're going to learn this in week number 7. Week number 7, inshallah. Okay, so if you base on this equation to find the H, there are three main things that you need to understand, we need to obtain, which are the current magnitude, the dl vector. Okay, dl basically will be based on the systems of coordinate. Yeah, remember this dl that I mentioned to you just now, this dl. So it will be used here, yeah, this dl vector. And then you need to find the vector of r, which is the position vectors from your source, from the current to the point of interest. That should be the vector of r, yeah? So if you base on this equation, we need to choose suitable systems of coordinate for us to substitute the dl vector values or dl vector components and also the r vector components. Yeah, so we need to choose the suitable dl vectors, yeah, the suitable dl vectors and the suitable r vectors. Okay, so we cannot simply use any system of coordinates. So we need to be based on the given problems here. So if we base on this diagram, we know that we have a cable which is in cylindrical form. So obviously the proper or the suitable systems that need to be applied here will be a cylindrical systems of coordinate. So once you have agreed that we need to apply the cylindrical systems, then you can use the proper dl and the proper r to be substituted in this equation for us to find the H field. Okay, so that's the first motivation. Yeah, so very important. I just want to remind you that it's very important for us to understand the proper use of systems of coordinate in solving the EMT problems. And second problem is that we want to analyze the electric field or the magnetic field induced by the antenna. Okay, for instance, yeah, we have this antenna here. For instance, this is your antenna. Okay, it will emit a signal. Yeah, emit a signal, EMT signal, and we can find basically the electric field. For instance, yeah, E field at this particular point of A. We can find the E field at the point of B. We can find the E field at the point of C. Okay, so to find the electric field, yeah, electric field at the point A, B, or C, we need to use specific equations to find the E field, in which the equation that shall be applied will be E field shall be equals to integrations of dq, yeah, of r vectors divided by 4 pi r power of 3. So this is based on the equations of Coulomb's law. Yeah, Coulomb's law. So we're going to see these equations in lecture number 4 later on. Yeah. So if you base on this equation, there are two main things to be obtained prior to calculation of E field. The first one will be a dq, which is the charge element, and then the vector of r, which is the position vector. So position vector will be positioned from the source. Yeah, this is the source, position from the source to the intended location. So the vector of r in these examples will be the vector, position vectors from the source to the point of A, which will be the vector of r, from the source to the vector of B, vector of r, and the source to the point of C, which is the vector of r. Okay, so that should be how we calculate the vector of r. So in calculating the vector of r, which is similar to the case of first problem just now, this R should be based on the proper usage of systems of coordinate. Yeah, system of coordinate. So we need to choose suitable system of coordinate to be applied in this particular problems. Okay, and basically if we have a space like this, yeah, a space, so the suitable systems to be applied should be a spherical systems of coordinate. Yeah, spherical systems of coordinate. So I think it's good enough for us to cover these two examples, just for us to understand why it is important for us to apply or learn about the systems of coordinate in which these will be used in solving the EMT problems later on. Yeah. Right. So I can now proceed with the important parameters of systems of coordinate. The first one will be the differential length, the DL, in which the DL can be in two forms. It can be in a scalar form or it can be in a vector form. And I put here the examples where we're going to use this DL. And for instance, in chapter 4, when we learn about the potential, electric potential, this is where the DL will be applied, where we have V equals to E dot DL. Yeah. So depending on the systems of coordinate, you need to apply suitable DL in solving the potential here. Okay. The same things apply for the second parameters, which is the differential area, the ds. Yeah? So the ds can be in a scalar form or it can be in a vector form. For instance, we use this ds in chapter 3 when we learn about the Gauss law. So Gauss law is the second law that can be applied in calculating the electric field intensity, the E field. Where the equation states that the closed surface integration, I forgot to put closed surface here, yeah, it's supposed to be closed surface integration. The d dot ds should be equal to the enclosed charge. So this is where the ds has been applied. Okay, so again, you need to adopt suitable ds vectors in solving this equation, depending on the given problems. Yeah? And finally, for the differential volume, the dV, okay, the dV. So dV, the differential volume will just be a scalar component. And the application for this, for example, so I put it here in the Coulomb's law. Yeah, in the Coulomb's law, yeah, chapter 2 that I mentioned just now. So we have E vectors as integration of rho v dV of 4 pi epsilon naught r squared in the direction of r. Yeah, in the vector of r. So this is the examples where we apply the Coulomb's law, where we apply the dV in EMT. Yeah. Okay, so there are three main parameters. I just repeat it. We have a DL, we have a DS, and we have the dV. So all of these systems of coordinate will be having their own DL, DS, and dV. So our task now is to actually figure out, yeah, just figure out what are the DL, DS, and the dV for all of these systems of coordinate. Yeah. Okay, so let us proceed with the first one, which is the rectangular system. Okay, for rectangular system, normally we represent it by the Cartesian x, y, and z axis or component. Yeah. And in order for us to define the DL, DS, and dV, we need to sketch a small box that we have sketched here, yeah, in which we sketch the box such that we are going to have a very small element which are said to be parallel with regard to each axis in the Cartesian systems of coordinate. For instance, we have this side, yeah, this side, which is said to be parallel with the x-axis. So we define it to be a dx. So dx is a small change of length, yeah, a small length component that is parallel with the x-axis. And similarly, for this length, yeah, for this length, which is parallel with the z-axis, so we call it as a dz component. And then for this component, which is parallel with the y-axis, so we call it as a dy. Okay, so in general, we can write that the dl vector, yeah, the dl vector for the Cartesian system, in general, we can write it simply as dx direction of x plus dy direction of y plus dz direction of z. So that should be our dl vector, yeah, with regard to this Cartesian system. Yeah. Okay, then we go for the ds for respective surfaces. Let's say we have surface C. Surface C, if I can label it here, that should be our surface C. So for surface C, the ds will be a multiplication of the side. So surface C is basically the area of surface C can be calculated by multiplication of dx and dz. Yeah, so we have ds as dx and dz. For surface D, the top here is defined by the elements of dx and also dy. So we have dx multiplied with dy. And for surface E, this surface in front here, so it is defined by element of dz and element of dy. So we have ds as dy dz. Okay, so that should be the area of ds. Yeah. So there is a sorry for this. There is a student that wish to enter the class. Okay, let's go back to this slide. Sorry for the interruption just now. Yeah. Okay, so we go back to this calculation. Let's say the ds for surface number C. If I can rewrite for you, we have dx, we have dz. For ds will be for surface D, yeah, dx and dy. And for surface E, it should be dy and dz. Yeah. Okay, and dl just now we can have it as dx of x plus dy of y plus dz of z. Okay, this is in terms of the magnitude of the area for surface C, D, and E. But for the vector of ds, yeah, vector of ds, so we have another section here, the vector of ds. So we call this as a surface vector. Yeah, ds here we call this as a surface vector. Okay, surface vector, in which the surface vector basically is defined by the area, yeah, the area for that particular surface, and the vector of it basically will be a vector which are said to be normal and away from the structure. For instance, if we base on the surface C here, the surface vector for surface C will be having a vector which is in this direction, because in the vector here is said to be away from the box. Yeah, away from the box. So for surface C, the ds should be given by the magnitude, which is similar to this ds just now, which is dx dz, but the unit vector for this ds will be similar to y direction. So we're going to have it as y unit vector. Okay, right. And for surface D, yeah, surface D, the ds should be given by, again, the magnitude will be the same, dx and dy, but for surface D, unit vector will be in this direction, which is normal and away from the box. So what should be the unit vector for this? It should be direction of z. Yeah, it should be direction of z. And then for surface E, you are going to have ds as dy dz, and the vector for it will be in this direction, which will be in the direction of x. Yeah, so that should be the direction of unit vector for surface E in terms of its surface vector. Okay, I hope it's clear. And if we consider another surface, for instance, yeah, another surface, let's say the surface is located opposite with surface C, yeah, given here, the structure then. Okay, so for this particular surface, okay, the surface vector for that particular surface should be given by the area, which is dx dz, and in the vector for it will be opposite with the y, which will be negative of y direction. So that should be surface vector for the surface here, which is opposite to the surface of C. Okay then? Okay, so the same things apply for all the surfaces in this particular structure. Right, and finally the dV. So for now we have calculated the dl vectors, the ds for the Cartesian, and finally for the differential volume, the dV, it can be then returned as simply as dx, dy, and dz. So we just multiply all the components in the box so that we can calculate the volume of the structure here. Yeah, so dx multiply with the dy multiply with the dz. So that should be the dV. Okay then, any question for this Cartesian systems of coordinates? Any questions so far? No, yeah? Okay, if there's no question, I think we can proceed to the second one, which is the cylindrical system of coordinate. Oh, sorry. So we have the cylindrical systems. Okay, so for this system of coordinate, cylindrical, it is defined by three axes, or represented by 3 points, yeah, 3 coordinates, which is r, p, and z. Yeah, so any point which is defined or which is based on these systems will be having a point defined by r, p, and z. So what is meant by this r, p, and z? Okay, so if you base on this diagram, yeah, still we can say that our coordinate of cylindrical will be based on the Cartesian as its basic structure. Yeah, so we have x here, we have y there, we have z still. Right, but in terms of the point, yeah, in terms of the point, we can see that if we define this point here as the point of r, p, and z, yeah, which is represented using the systems of cylindrical coordinate. Yeah. Okay, what is meant by r? So r is defined by the radius. Which is measured starting from the z-axis. So that should be your r, yeah, which is the radius. And as such, unit vector for the r will be given by this unit vector of r, which is always perpendicular with regard to the cylindrical surface. Yeah. For instance, if I define the point here, so my r unit vector should be in this direction. If I define the point here, so my r unit vector should be in this direction, in which is always perpendicular with regard to the cylindrical surface. Yeah. Okay, and then what is phi? So phi is measured starting from the x-axis. So which means that if I can project this point downwards up to the plane of xy, yeah. So this is the plane of xy, yeah, plane of xy down here is the plane of xy. So if I project this point downwards to the plane of xy, and I connect the point to the origin, so I can have one dotted line there. This is my dotted line. So my phi angle basically is measured from the x-axis to that particular line. Okay, so that should be my phi angle. If my point is here, yeah, yes, my point is here, and if I project it downwards to the xy plane, so my phi will be this angle. Okay, that should be my angle then, yeah. So I hope that you can define, you can now understand what is the definition of the angle phi for the cylindrical systems, yeah. And then for the z, which is the height, so the height is measured from the xy plane, yeah, the height is z is measured from the xy plane. And if we can see that based on that, the z is measured here, so that should be the z, yeah, the height of the point from the xy plane. Okay, I forgot to explain about the unit vector. Okay, since we have the phi is measured starting from the x-axis, yeah, in the counterclockwise direction. So the unit vector of phi basically will be in tangential direction with regard to the point. Yeah, for instance, if the point is here, So the phi unit vector will be in a counterclockwise direction, but it is tangential. The same things applied. If we have the point here, so your phi, okay, I believe that you're going to have the phi down here. Yeah, that should be the angle of phi. If they can project to the origin, so my phi should be here. So unit vector of phi for this particular point will be tangential and in this direction. So that should be unit vector of phi with regard to that particular point. Okay, so phi must always be a tangential unit vector with regard to the surface of your cylindrical structure. Okay, and for the z unit vector, since we know that the point is here, so the z should be directed upwards. I can see that the z unit vector for the cylindrical system is almost similar with the unit vector for the Cartesian system. Yeah? Okay, so let's have a look on the range, allowable range for the R. So R should be having a range or allowable to be, is allowed from 0 to infinite. That should be the allowable value for the radius of R. For the phi, yeah, for the phi, which is the angle here, starts from 0 at the x-axis, and it can be, because for a full cylinder, it can be a clockwise, counterclockwise direction. We make a full circle and go back to the x-axis, and then going to have the phi will be having a range from 0 to pi. And for the z, yeah, the value of z for this cylindrical system, it can be having a range from negative infinite to a positive infinite, yeah, because your cylindrical structure can be extended to negative infinite and to the positive infinite values. Okay, so that should be the range of R, phi, and z, and that should be your vector in cylindrical systems of coordinate. Yeah. Okay, so once you have understand this, we can then proceed with obtaining the dl, ds, and the dv for cylindrical systems. So in order for us to define these dl, ds, and dv, we need to obtain, or we need to sketch a small box. So the small box can be written to be like this, but basically it's actually obtained from a piece of the cylindrical structure. So if we can sketch it like this, so basically we are taking it up from this particular structure, yeah? We're taking it out. Okay, so that should be the case. Huh? So we take it out from this cylindrical structure and we have this box. Okay, so why we have dr, why we have r, d phi, and why we have dz as the element of the box here. So if I can sketch this piece of cylindrical structure, yeah. Okay, so we have this particular structure. Sorry, not nice, not very nice, my drawing. Okay, hopefully it's okay lah. Okay, this is the radius of R. R is the radius, yeah. R is the radius, yeah. So we have a small change of the radius. So we call this as a dr. Yeah. So a small change of the radius will give us dr. We have the angle of phi here. So a small angle here will be a d phi. That's why this length, this curve of the length of this curve will be equals to r d phi. Okay, r d phi. And the z is the height, so a small change of the height will be the dz. So that's why we have dr, we have r d phi, and we have dz as the element of the box. Okay. All right. So let us define the dl, ds, and the dv for this system. Okay. In general, we can write that the dl for cylindrical systems can be written as dr of r, because this will be in, it will be following the direction of r, the radius in the vector. And then we have for r d phi, which is this length, basically it follows in the vector of phi direction. So that should be r d phi direction of phi. Whereas for the dz component, it will follows the Z in your vector. Yeah, Z in your vector, so it should be dz direction of Z. So that should be the DL vectors, the differential length vectors for cylindrical systems of coordinate. Yeah. So we have dr of r d phi of phi, and dz of Z. And then for the ds we need to base on the surfaces. Yeah, based on the surfaces. Okay, let's have a look at this surface. Let's say surface number A on top here. Now surface number A, we can see that the ds for the surface number A or surface A will be simply a multiplication of the elements, which will give us r dr d phi. Yeah, dr multiplied with r d phi will give us r dr d phi. For surface B, okay, we have the ds shall be equals to dr multiplied with dz, so we have dr dz. Whereas for surface C, we are going to have the ds to be equals to r d phi multiplied with dz. So that should be the area, yeah, the ds for surface A, B, and C with regard to the given box here. But in terms of the surface vector, so we have for surface A, the ds vector, sorry, yeah, surface vector for surface A, okay, we are going to have the unit vector for surface A will be in this direction. Yeah, remember the definition of surface vector, in which the unit vector must always pointed normally with regard to the surface, normal with regard to the surface, and is away from the structure. So if you base on this unit vector, and if we compare with the unit vector we have here in this diagram, in the big diagram here, we can see that this unit vector will be in the direction of Z. Yeah, so we have r dr d phi direction of positive Z. Okay, and for the surface of B, this surface, you're going to have the ds vector. It will be dr dz in terms of magnitude, but the unit vector for it will be in this direction. Yeah, this is Z direction. So if you base on this diagram, what should be the direction of surface vector for surface B? So if you base on this, we can see that phi is pointing in the counterclockwise direction. So this direction will be negative of phi direction. So we have it as negative of phi direction. And finally, for surface C, we have the ds vector will be r d phi dz, and your vector for surface C will be in this direction, which is normal. And obviously, we can say that the direction of vector for surface C will be in the direction of r. So we're going to have it as positive r direction for surface C. Yeah. So if we have, let's say, if I have another surface, let's say I have this surface. Okay, this surface at this side, which is in opposite to the surface B. Yeah, opposite to the surface B. So we can see that for that particular surface, the ds vector will be similar to surface B in terms of the magnitude, which will be dr dz. But in terms of unit vector, it will be in this direction, in which the direction of this will be opposite to negative phi, which will give us phi direction. So that should be the ds of that particular surface, which is opposite to the B surface. Yeah. Right. So we have done with the dl, we have done with the ds, and finally the dv. So dv will be straight away we can just multiply all the elements in this box. So we have dr, we have r d phi, we have dz. So the dv will be r, dr, d phi, and dz. So that should be your dv for these systems of cylindrical coordinate. Okay then, any questions up to now?
Excuse me, doctor.
Yes.
Under the surface, it is the ds only dr dz.
Come again. I cannot get you. Which one?
Sorry.
Yeah,
For the B surface, is it the ds equal to dr dz?
correct.
Dr dz, yeah. Okay.
Yeah, dr dz, yeah.
And for the ds vector?
For the ds vector, okay, so if you base on the surface B, am I right? Surface B, yeah?
Mm-mm.
Surface B, what should be the direction of these vectors then?
Okay.
So
Alright.
it should be negative phi, yeah, because opposite to this phi. Lah. So
Negative,
phi
yeah.
is always, yeah. Phi is always in counterclockwise direction. But when we have this surface B, the direction is negative phi. Yeah? Okay, thank you for the questions.
Thank you.
Okay, I think we can now proceed with the final system of coordinate, which is spherical. So for spherical, again, we are still using the framework of XYZ Cartesian system. We have X here, yeah, we have X here, we have Y, and we have Z. So for spherical systems, any point using the spherical system can be represented by the point of R, theta, and phi. Yeah, R, theta, and phi. Some books use the R as rho, yeah. Some books use rho, but I prefer to use R instead of rho because rho is normally we use as a density, yeah, as a density representation. So I prefer to use R instead of rho to be used as a radius, yeah. So again, for spherical systems, the point is represented by R, theta, and phi. So if we base on this diagram, so what we have here is part of your spherical structure. Yeah. So if I have this particular point here, the point of H here is given by R, theta, and phi. What is R? R is given by the radius of the point and is measured from the origin. Yeah, R is measured from the origin. As opposed to cylindrical just now, for cylindrical, R is a perpendicular radius, yeah, perpendicular radius with regard to the z-axis. So two different things then, yeah. So R in cylindrical and R in spherical are totally different, yeah. Okay, so go back to spherical system. So R in spherical is a radius which is measured from the origin. Okay, and for that, we can say that unit vector for the R will always pointed perpendicular with regard to the surface of your sphere. If we consider the point here, let's say this is your R, that's your R. So unit vector of R for this particular point will be in this direction. Yeah, so depending on at which particular point that you are referring to. And if we consider at this particular point, so that should be the R. So in the vector of R should be in this direction. Yeah, so remember R in the vector must always be perpendicular with the surface of your sphere. Okay, then we proceed with the theta. Okay, so for the theta, okay, sorry for this. Okay, for the case of theta, theta is the angle which is measured starting from the z-axis. Yeah, starting from the z-axis, we are measuring this theta, and it is bounded by the radius of R. Okay, so because your point is here, right? The point is here, the point of H. So the theta will be measured starting from the z-axis up to the radius. So that should be the boundary for the theta. If your point is here, so your theta should be measured starting from this z-axis up to this radius value. So this is your R radius. So your theta should be this one. Okay, so hope that you can understand what is the theta, how you measure the theta. Yeah, so the theta is measured starting from the z-axis, and it should be ended at the negative z-axis. Yeah, so starting from z and ended at the negative z-axis. Whereas for the phi, yeah, for the phi, yeah, R, theta, and phi. So R is the radius, theta is measured from the z-axis. Whereas for the phi is actually the angle which is measured starting from the x-axis, in which it can be measured if we project this point of H to the xy plane. Yeah, we project the point to the xy plane. So we have these dotted lines down here. Yeah, when we project the H point to this XY plane, so we're going to have this line. So the phi angle is measured starting from the x-axis up to that particular line. So that should be the phi. Yeah. If your point is here, for example, if your point is here, so if we project this point to the XY plane, so you are going to have the phi angle which is measured starting from the x-axis up to that particular radius line. So that should be the phi. Yeah, that should be the phi for this point here. Okay, so I hope that you can distinguish the r, the theta, and the phi. And in terms of unit vector, yeah, because if you base on theta here, r has been explained just now. For the case of theta, because theta is measured starting from the z-axis, yeah, so we can see that the theta unit vector will be a tangential unit vector, but pointing downward, which is following the direction where the theta is said to be measured. So if, for example, if your point is here, so the theta will be in this direction. Okay. If the point is here, so your theta will be in this direction. If your point is here, so your theta will be in this direction. So theta will always be in tangential and pointing downward. Okay. And for the phi unit vector, we can see that again, phi will be a tangential unit vector as shown here in the diagram, but it is measured in the counterclockwise direction. For example, if your point is here, so the phi for that particular point will be in this direction. Yeah, that should be the phi direction. And also if your point is here, the phi should be in this direction, which must always be tangential, but in the counterclockwise direction. Okay, so that's how we define the r unit vector, the theta unit vector, and the phi unit vector. Okay, about the range for the r, theta, and phi, and based on this diagram, you can see that r will be having a range from 0 to infinite, which is the allowable range. Theta will be having a range from 0, starting point here at z-axis, and it will end up at the negative z-axis. So the range of theta will be from 0 to pi, yeah, 180. And for the phi angle, you're going to have a starting point at x-axis, which is at 0. And for a full sphere, it should be having a full clockwise direction, or complete clockwise direction, counterclockwise direction, sorry, which will be having a range from 0 to 2 pi. Okay, so that should be the range that is allowable for the r, theta, and phi in the spherical systems of coordinate. Yeah? Okay then, so in terms of the dl, ds, and dv, okay, right, so what we have here is the box that have been taken out, yeah, from this particular spherical structure. But allow me to resketch it for you on how we get this box from the structure here. So basically what we did is that we are taking out the structure from a sphere, yeah, this structure, okay, and we are taking it from this particular section, okay. So that should be a taken section. So if we can enlarge it here, yeah, I want to enlarge it here, so that should be the case. Okay. Okay, I hope I make it clear to you on how we get this particular structure. Yeah, so this is the origin. Yeah, this is the origin, right? Okay, so let us define how we get this: the r d theta, and r sin theta d phi. Okay, r is the radius. So if you can see that this is your r, the radius of r. Yeah, that's the r, the radius. I need to use another color then. Sorry for that. Okay, the black color should be better. So r is the radius here. So a small change of the radius, yeah, a small change of the radius. So this is your dr, yeah, that's your dr, a change of the radius. And we know that this is your z-axis, yeah, z-axis is here. right? Right, and we know that the theta is here. That's your theta. Yeah, that's your theta. So there should be a small change of theta here. Am I right? Your theta is here, so that should be a small change of theta, and we call this as d theta. So that's why this section here will be having a length of r d theta. Okay, that's why we have r d theta here, yeah, because all this side here will be r d theta, yeah, same length of r d theta, yeah. And finally, for the third section, this element, how we get it as r sine theta d phi. So we know that by using a sine, yeah, using a sine, we have r here, we have theta here, so this length here will be equals to r sine theta. Yeah, if we can enlarge it, we have theta, we have r, so this will be r sine theta. Yeah, so that length here that we have drawn here will be r sine theta, and we can see that this small angle here will be a change of your phi angle. So the phi is here, so that should be a small change of the angle phi, so that will give us the phi angle. And as such, we can see that this length here will be simply r sine theta multiplied with the d phi. So we have as r sine theta d phi. So that's how we define this element as r sine theta d phi. Yeah. Okay, so I hope I make it clear to you on how we are getting these elements of the box. Yeah. Okay, so let us define dl, ds, and dv. So basically, if we base on the previous explanation, we can see that dr is related to the r in a vector, r d theta is related to the theta in a vector, and r sine theta d phi is related to phi in a vector. Yeah, so this is the relationship with this. Dr is related to r, and r d theta is related to the theta. So based on that, we can say that your dl vector should be equals to dr direction of r plus r d theta direction of theta plus r sine theta d phi direction of phi. Yeah, so that should be the general terms of dl vectors for spherical systems of coordinate. Okay, all right. But in terms of the ds, yeah, in terms of ds, we need to consider the surfaces. Yeah, surfaces. All right, so for the surfaces here, we have, let's say we have surface A here, surface A, surface B, and surface C. Okay, so for surface A, we can define that the area for surface A, the ds will be just a multiplication of the elements, where we have it as r squared, yeah, sine theta, d theta, d phi. R d theta multiplied with this will give us r squared sine theta, d theta, d phi. Yeah? For surface B, the surface will be just multiplication of dr and r d theta. So we can realign it to be r dr d theta. Yeah, this dr, and this is r d theta. So when multiply, we're going to have r dr d theta. And then for surface C, the top here, it should be dr multiplied with r sine theta d phi. So we are going to have it as r sine theta dr d phi. Okay, so that should be the area for respective surfaces of the box A, B, and C. Okay, so once we have this, we can straight away find the surface vector. For instance, for surface A, the ds vector will be having similar magnitude, r squared sine theta d theta d phi. But in terms of its unit vector, it should be pointing outwardly from your box. So that should be in this direction, which is in normal direction. So if we compare with this particular structure just now, knowing that this is in perpendicular with regard to the spherical surface, we can see that this is in the direction of r. So for surface A, the ds should be in the direction of positive r. Okay, for surface B, yeah, the ds vector will be having similar area, which is r dr d theta, but the vector for surface B will be in this direction, in which if we compare with this spherical structure here, we can say that unit vector for B will be opposite to the phi unit vector, which will give us negative of phi direction. So that we're going to have negative of phi for the surface vector direction for surface B. And finally, for surface C, the ds will be having similar area, which is r sine theta, dr d phi. But looking at this surface C, the unit vector will be in this direction, which is upward, as compared to the theta, which always pointing downward. So this direction will be negative of theta. So we have it as negative of theta for surface C. But if we consider another surface, let's say there's one surface located opposite to the surface C, for instance. Yeah, we have surface down here, which is opposite to surface C. So for this particular surface, the ds will be similar in terms of the magnitude, which is r sine theta dr d phi, but unit vector for this particular surface will be opposite to that, in which it will follow the direction of theta. So for that particular surface, unit vector for it will be direction of theta. The same things applied for all the surfaces in this particular box. Okay, so that's how we define the ds for spherical systems. And finally, the dv, as usual, the dv will just be a multiplication of all the elements in the box. So it's going to have it as r squared sine theta dr d theta d phi. So that should be your dv for spherical systems. Yeah, you just multiply r d theta, r sine theta d phi, and dr, and we're going to have it as these particular terms here. That should be the dv. Yeah. Okay, any questions for spherical systems of coordinate on the dl, ds, and dv derivation? Okay, so I advise you to understand these topics fluently, I can say, because as I mentioned earlier in this lecture number 2, we're going to use these systems of coordinate regularly in this course. Yeah, so always going back to this box. Yeah, always go back to this box. This box for cylindrical. Yeah, and also the box for the Cartesian. But Cartesian thing is not that critical. Critical will be on these cylindrical systems and spherical systems. Yeah, because this will help you in understanding, in identifying which ds should be applied if we are given the EMT's problem. Okay, so that will be the end of lecture number 2. We are going to start our EMT lectures, the actual EMT, this Wednesday, inshallah, 2 o'clock, in which it will be covered in lecture number 3 on the topics of electrostatic charges. This is on lecture number 3. And for these 2 topics, electrical intensity and Coulomb's law, will be covered in lecture number 4. So this will be covered in our class on Wednesday. Right. Is there any question before we end the class today?